This lecture is about measurement errors in a linear regression model. So most economic data consists of imprecise measurements. The difference between the true value and the measured value is the measurement error. For example, macroeconomic data has measurement errors since it's not possible to accurately measure every activity in the economy. Survey data has measurement errors because respondents make mistakes filling out the form and they may provide information that may be the best to their knowledge. Few people would know, for example, the exact yearly income from last year. So we can denote the variable that we try to measure by z. This is a true but unobserved variable. And we can denote the measurement of z by x, and x is observed. That's what we measure. So the measurement errors is then the difference between x and z. So to formalize this a little bit further, let's consider a linear regression model with just one single explanatory variable. And let's say that we have data, we have a random sample, y data, the dependent variable, and x data, where the x data are measurements. And we assume that these measurements of the z data, they have measurement errors. Now the dependent variable may or may not have measurement errors as well, but to simplify things a little bit, let's for the moment assume that the dependent variable does not suffer from measurement errors. So for a concrete example, let's say that we've made a survey and we've asked some individuals about their income last year, and we have also asked them about Y data, which could be the size of the apartment or of the house that the family lives in square meters. So the income more reasonably would be than the family income. Now, if we want to make a connection between the square meters and income, it's reasonable to assume that it's the actual, the true income of the family that determines the y variable and not the reported income. So it's reasonable to specify that the conditional expectation of y depends on z and not x. So even if I condition on both the true income and the reported income, the expected value of y will only depend on the true income. What we have reported has no additional information about the true income. So an interesting question is then the following. What will be the consequences of using an explanatory variable that has measurement errors? Unfortunately, the answer is as follows. The OLS estimators B1 and B2 will both be biased and inconsistent. This will actually be true even if the measurement errors on average is zero, so that some respondents report a higher income than they actually have, and some respondents report a lower income. Even in such a case, the OLS estimators will be biased and inconsistent. If we have no measurement errors in the explanatory variable, then the x variable and the z variable will coincide, and in that case we will have an exogenous x variable, and the OLS estimator will be unbiased and consistent. So it's probably not too hard to buy that the worse the measurement errors, the bigger is the bias and inconsistency. It's actually possible to show that if I have one explanatory variable, the bias will always go in one direction, and the direction is towards zero. So for example, if beta 2 in reality is equal to 1, then the expected value of B2 may be something like zero point 0.8, something closer to 0, less than beta 2 if beta 2 is positive. If beta 2 is negative 1, then the expected value of B2 may be something like minus zero point 0.8, again attenuated towards 0. The consequences of measurement errors in this model with one explanatory variable is therefore underestimation of the marginal effect of x on y if beta 2 is positive. If we extend this model to a case with several explanatory variables, the result will then be as follows. If at least one of the explanatory variable has measurement errors, it is actually enough that one of them has measurement errors, then all of the OLS estimators will be biased and inconsistent. This attenuation towards 0 is often still true, but it cannot be proved to hold in every case. So we will later on discuss some methods of handling this problem of measurement error in the explanatory variables, but in general it's a problem that's very hard to deal with. Turns out that you do need some additional information in order to handle measurement errors problems. So as econometricians, in order for us to be able to rely on the results of our econometric studies, it is important that we try to keep measurement errors as small as possible in our data. Now you can also have measurement errors in the dependent variable, and that is not as big a problem. If you have measurement errors in the dependent variable only and not in the explanatory variables, then the OLS estimator is still going to be unbiased and consistent. The effect of having measurement errors in the dependent variable will simply be to increase the standard errors of your OLS estimates, but you keep them unbiased and consistent. And that means then, of course, that the inference that you're able to make will not be as precise as if you had no measurement errors in the dependent variable.